Section 250.66 of the National Electrical Code requires a grounding electrode conductor to be installed with service conductors. This conductor connects the service disconnect enclosure to the grounding electrode system. The proximity of the utility meter base to the transformer does not waive this requirement. The grounding electrode conductor must be installed within the same raceway, cable, or trench as the service conductors. It must be of the same material, copper or aluminum, and sized according to code requirement. The minimum size allowed for the grounding electrode conductor is 6 American wire gauge. The purpose of the grounding electrode conductor is to provide a low impedance path for fault current. This path allows the fault current to return to the utility grounding system, mitigating the risk of electrical shock and preventing equipment damage in the event of a fault. While the code does not explicitly require a separate bonding conductor alongside the service conductors, the grounding electrode conductor effectively serves as both a grounding conductor and a bonding means. It connects the service disconnect enclosure to the grounding electrode system, fulfilling both functions. Therefore, when installing a 200 amp service, the National Electrical Code necessitates the installation of a grounding electrode conductor alongside the service conductors, irrespective of the utility meter base's location. The grounding electrode conductor must reside within the same raceway as the service conductors and be appropriately sized according to code specifications. To summarize, the key aspects are: firstly, the National Electrical Code Section 250.66 mandates a grounding electrode conductor or GEC to be installed with service conductors to connect the service disconnect enclosure to the grounding electrode system. Secondly, the location of the utility meter base near the transformer does not exempt the installation from this requirement. Thirdly, the GEC must be installed in the same raceway, cable, or trench as the service conductors. It must be of the same material and size as the service conductors, with a minimum size of 6 American wire gauge. Fourthly, the GEC provides a low impedance path for fault current to return to the utility grounding system. This helps protect against electrical shock and equipment damage in the event of a fault. Fifthly, the code does not specifically require a separate bond conductor to be installed with the service conductors. The GEC serves as both a grounding conductor and a bonding means connecting the service disconnect enclosure to the grounding electrode system. When installing a 200 amp service, you must install a grounding electrode conductor with the service conductors. This applies regardless of where the utility meter base is located. Ensure the grounding electrode conductor is within the same raceway as the service conductors and is sized correctly. Let's elaborate on the sizing requirements for the grounding electrode conductor or GEC. Section 250.66 provides a table to determine the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Since you are using 4/0 aluminum conductors, you will need to consult this table to determine the appropriate size of the grounding electrode conductor. Keep in mind that the grounding electrode conductor must be of the same material as the service conductors, in your case aluminum. The connection of the grounding electrode conductor to the grounding electrode system is also crucial. Common grounding electrodes include ground rods, ground plates, and metal washer pipes. The grounding electrode conductor must be connected to the grounding electrode using approved methods such as exothermic welding or listed connectors. The location of the grounding electrode is also important. It should be accessible and protected from physical damage. The code specifies requirements for the depth and placement of ground rods. When running the 4/0, 4/0, 2/0 aluminum underground, be sure to use direct burial rated conductors or conductors in a suitable raceway. The minimum burial depth for underground service conductors is specified in the code. The type of raceway used, such as rigid metal conduit or PVC conduit, will also affect the required burial depth. It's always a good practice to consult with the local electrical inspector to ensure compliance with all applicable codes and regulations. They can provide guidance on specific requirements in your area and help you avoid potential problems. Remember, proper grounding is essential for electrical safety. It protects people from electrical shock and helps prevent damage to equipment. Always follow the code requirements and best practices when installing a grounding electrode conductor. When selecting the appropriate size for the grounding electrode conductor, based on the 2023 National Electrical Code, refer to Table 250.66. This table provides the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. In your case, with 4/0 aluminum service entrance conductors, Table 250.66 will dictate the minimum size aluminum grounding electrode conductor required. It is crucial to consult this table directly in the 2023 National Electrical Code to obtain the precise size. For example, if Table 250.66 indicates that for 4/0 aluminum service entrance conductors and 4 American wire gauge aluminum grounding electrode conductor is required, then you must use at least 4 American wire gauge aluminum. Always refer to the specific edition of the National Electrical Code adopted by your local jurisdiction, as requirements may vary. Also, ensure that all grounding connections are made using approved methods and materials listed for the purpose. This includes using appropriate connectors and ensuring proper bonding techniques are employed. Maintaining a low impedance ground fault path is paramount for electrical safety and proper system operation. Always consult with a qualified electrician or electrical inspector if you have any questions or concerns regarding grounding requirements. Understanding the function of the grounding electrode conductor, or GEC, is vital for grasping its importance. The GEC serves as a critical safety component in an electrical system. Its primary function is to provide a low impedance path for fault current to return to the source, typically the utility transformer. This low impedance path facilitates the rapid clearing of ground faults by overcurrent protection devices, such as circuit breakers or fuses. In the event of a ground fault, where a live conductor comes into contact with a grounded surface, the GEC provides a path for the fault current to flow back to the source. This high current flow causes the overcurrent protection device to trip, interrupting the circuit and preventing further damage or injury. Without a properly sized and installed GEC, the fault current may not be sufficient to trip the overcurrent protection device, resulting in a sustained fault condition. This can lead to overheating, fire hazards, and potential electrical shock. The low impedance characteristic of the GEC is essential for ensuring that the fault current is high enough to quickly trip the overcurrent protection device. A high impedance path would limit the fault current, potentially delaying the tripping of the overcurrent protection device and increasing the risk of hazards. Furthermore, the GEC also plays a role in stabilizing the voltage to ground during normal operation. It helps to minimize voltage fluctuations and ensure a stable reference point for the electrical system. This is particularly important for sensitive electronic equipment that can be affected by voltage variations. The NEC mandates the installation of a GEC to ensure that all electrical systems have a reliable and effective grounding path. This is a fundamental safety requirement that helps to protect people and property from the hazards of electrical faults. Consider the materials acceptable for the grounding electrode conductor. Grounding electrode conductors are typically made of copper or aluminum. The selection of material depends on several factors, including cost, conductivity, and corrosion resistance. Copper is a widely used material for grounding electrode conductors due to its excellent conductivity and corrosion resistance. It provides a low impedance path for fault current and is less susceptible to corrosion than other metals. Aluminum is another option for grounding electrode conductors, particularly in applications where weight is a concern. Aluminum is lighter than copper, making it easier to handle and install. However, aluminum has a higher resistance than copper, so a larger size conductor may be required to achieve the same level of conductivity. When using aluminum grounding electrode conductors, it is essential to ensure that all connections are made with listed connectors suitable for use with aluminum. Aluminum connections are more prone to corrosion than copper connections, so proper installation and maintenance are crucial. The NEC specifies the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. These requirements ensure that the grounding electrode conductor has sufficient capacity to carry the expected fault current. The grounding electrode conductor must be protected from physical damage and installed in a manner that minimizes the risk of corrosion. It should be run in a direct and unobstructed route to the grounding electrode. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding or listed connectors. The grounding electrode itself must be of a type recognized by the NEC, such as a ground rod, ground plate, or a metal water pipe. In summary, the material selection for the grounding electrode conductor depends on several factors, including cost, conductivity, corrosion resistance, and weight. Both copper and aluminum are acceptable materials, provided that they meet the requirements of the NEC and are installed in accordance with the manufacturer's instructions. Now consider the installation requirements of the grounding electrode conductor. The grounding electrode conductor must be installed in a manner that ensures its effectiveness and protects it from damage. The NEC specifies several requirements for the installation of grounding electrode conductors, including the following. Firstly, the grounding electrode conductor must be securely connected to the service disconnect enclosure. This connection must be made using approved methods, such as a lug or connector listed for the purpose. Secondly, the grounding electrode conductor must be protected from physical damage. It should be run in a conduit or other protective covering if it is exposed to physical damage. Thirdly, the grounding electrode conductor must be installed in a direct and unobstructed route to the grounding electrode. Avoid sharp bends or unnecessary splices. Fourthly, the grounding electrode conductor must be connected to the grounding electrode using approved methods. Common methods include exothermic welding, listed connectors, and clamps. Fifthly, the grounding electrode conductor must be sized in accordance with the NEC. The size of the grounding electrode conductor depends on the size of the service entrance conductors. Sixthly, the grounding electrode conductor must be continuous. Splices are not permitted in grounding electrode conductors unless they are made using irreversible compression connectors listed for the purpose. Seventhly, the grounding electrode conductor must be accessible. It should be located in a place where it can be easily inspected and maintained. Eighthly, the grounding electrode conductor must be identified. It should be marked with a tag or label that indicates its purpose. The grounding electrode itself must be of a type recognized by the NEC. Common grounding electrodes include ground rods, ground plates, and metal water pipes. The grounding electrode must be installed in accordance with the NEC requirements. For example, ground rods must be driven into the ground to a depth of at least 8 feet. The grounding electrode system must have a resistance to ground of 25 ohms or less. If the resistance to ground is greater than 25 ohms, an additional grounding electrode must be installed. The installation of grounding electrode conductors and grounding electrodes is a critical part of ensuring electrical safety. Proper installation helps to protect people and property from the hazards of electrical shock and fire. Always follow the NEC requirements and best practices when installing grounding electrode conductors and grounding electrodes. And consider bonding versus grounding and why they are different. Bonding and grounding are two distinct but related concepts in electrical systems. Both are essential for electrical safety, but they serve different purposes. Grounding is the process of connecting an electrical system or equipment to the earth. The purpose of grounding is to provide a low impedance path for fault current to return to the source, which helps to protect people and property from electrical shock and fire. Grounding also helps to stabilize the voltage to ground during normal operation. Bonding is the process of connecting together all metal parts of an electrical system or equipment. The purpose of bonding is to create a lower impedance path for fault current to flow between the bonded parts. This helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electrical shock. Bonding and grounding work together to provide a comprehensive electrical safety system. Grounding provides a path for fault current to return to the source, while bonding ensures that all metal parts are at the same electrical potential. In the event of a fault, the fault current will flow through the grounding path and the bonding path, which will help to quickly trip the overcurrent protection device and prevent electrical shock. The NEC specifies requirements for both grounding and bonding. These requirements are designed to ensure that electrical systems are installed and maintained in a safe manner. It is important to understand the difference between grounding and bonding and to follow the NEC requirements when installing and maintaining electrical systems. Now, let's consider the impact of the 2023 NEC on grounding requirements. The 2023 edition of the National Electrical Code includes several changes that affect grounding requirements. These changes are designed to improve electrical safety and to address new technologies. Some of the key changes related to grounding in the 2023 NEC include, firstly, revisions to the requirements for grounding electrode conductors. The NEC has updated the requirements for the size and installation of grounding electrode conductors. These changes are intended to ensure that grounding electrode conductors have sufficient capacity to carry fault current. Secondly, new requirements for grounding of specific equipment. The NEC has added new requirements for the grounding of specific types of equipment, such as electric vehicle charging stations and energy storage systems. These requirements are intended to address the unique grounding challenges posed by these new technologies. Thirdly, clarification of the requirements for bonding. The NEC has clarified the requirements for bonding to ensure that all metal parts of an electrical system are properly bonded together. These clarifications are intended to reduce the risk of electrical shock. Fourthly, new requirements for ground fault circuit interrupters or GFCIs. The NEC has expanded the requirements for GFCIs to include additional locations and equipment. These changes are intended to provide greater protection against electrical shock. It is important to stay up to date on the latest changes to the NEC and to follow the code requirements when installing and maintaining electrical systems. The 2023 NEC includes several important changes to grounding requirements that are designed to improve electrical safety. Always consult the latest edition of the NEC and follow the code requirements when installing and maintaining electrical systems. Let's discuss the importance of consulting with local electrical inspectors. Consulting with local electrical inspectors is crucial when installing electrical systems. Electrical inspectors are responsible for enforcing the NEC and other local electrical codes. They can provide guidance on specific requirements in your area and help you avoid potential problems. Local electrical codes may vary from the NEC. Some jurisdictions may have additional requirements or may adopt different versions of the NEC. Electrical inspectors are familiar with the local codes and can help you ensure that your installation complies with all applicable regulations. Electrical inspectors can also provide valuable insights and advice. They have experience inspecting a wide variety of electrical installations and can help you identify potential problems that you may not have noticed. They can also offer suggestions for improving the safety and efficiency of your electrical system. Consulting with an electrical inspector early in the design process can save you time and money. By identifying potential problems early on, you can avoid costly rework later on. Electrical inspectors can also help you ensure that your electrical system is properly grounded and bonded, which is essential for electrical safety. To find a local electrical inspector, contact your city or county government. You can also find a list of certified electrical inspectors on the website of the International Association of Electrical Inspectors. Consulting with local electrical inspectors is an important part of ensuring that your electrical system is safe and compliant with all applicable codes and regulations. Electrical inspectors can provide valuable guidance and advice and can help you avoid potential problems. This discussion is for informational purposes only and does not constitute professional electrical advice. Always consult with a qualified electrician or electrical inspector before undertaking any electrical work.